All right, welcome everyone. In today's lesson, we're going to look at integration by parts for definite integrals. And so all of the techniques and all of the strategies that we kind of developed and looked at when we talked about integration by parts for indefinite integrals is still going to apply here. So really for the definite integrals, there's only going to be one extra step, and that's to do some sort of evaluation at the end. So let's see how the notation is going to look, and then we'll look at a few examples. So first of all, the notation. And there's two kind of slightly different ways we can kind of handle the evaluation. But all of the actual integration by parts work is going to be exactly the same. So we know with integration by parts, let's recall our formula first, our short version. So it says the integral of u dv, and that's the integral that we're trying to do, is equal to u times v minus the integral of v times du. So really the two slightly different ways we can handle the evaluation here, once we get ready to do the evaluation part of our definite integral, is we can either evaluate the u times v part and evaluate this remaining integral part. We can do that separately, which is option 1 here, evaluate separately. So there we've evaluated the u times v part, which is right here in the formula. And then we still have that remaining integral to do, but that we'll evaluate that as well. And we'll do the evaluation separately. And so there are benefits of using this approach, especially if that remaining integral is this remaining integral right here is a bit more complicated. There's a bit more work you have to do. If that integral is on the easier side, or there's not too many steps involved, our second option is to just kind of get through all the integration and evaluate everything at the end. And that's our second option here. Evaluate all at once. So whichever one you want to use is perfectly fine, but in this kind of this second approach, we wait. So we've calculated u times v. We subtract, we still have this remaining integral, and what we'll do is we'll actually go through and do this remaining integration. We'll find the antiderivative, and so we'll just have one big antiderivative here, and then we'll evaluate the entire thing all at once. So those are really our two options. We can kind of split up the evaluation, evaluate our u times v part, and then evaluate this remaining integral, or get all the anti-differentiation done out of the way, and then once you have all the integration done, that's when you evaluate. So either way is perfectly fine. Figure out which method you like better, and that's what you should use. You'll get the same answer regardless. All right, so let's try an example. We're going to try example 1, and we're going to evaluate the definite integral of the function 2x plus 5 over e to the 3x, and we're evaluating this from -1 to 2. So before we kind of go any further, let's rewrite this function as a product. And that'll just help with the actual integration by parts side of this. So that's really where we're going to start this, is we're just going to go through our integration by parts like we normally would. So to help, I'm going to write this as a product. So 2x plus 5 times e. And then instead of a fraction, it'll be e raised to the -3x. Now we need to decide, we're going to do integration by parts. So step 1 is we need to figure out u, and we need to figure out dv. And let's remember what our strategy is. So we write down our acronym, LIATE. We look at the two parts of our function. So what are they? Well, we have this 2x plus 5 part, and that's algebraic. And then we have this, this e to the negative 3x. That's an exponential part. And so the part of our function further to the left, if we remember our strategy, the part of our function further to the left, that's what we pick for u. And the part of our function further to the right, that's what we pick for dv. So we're going to let u equal the 2x plus 5. We're going to let the dv equal e to the negative 3x dx. And there we go. We've picked u, we've picked dv. Now we're ready to just kind of go through the motions of the integration by parts formula. All right, so let's do step 2 now, where we calculate du. So derivative of 2x plus 5 is 2, and then we multiply by dx. We need to calculate v, so we're going to do our integration here. So we're going to integrate e to the negative 3x, and this is one of our k-form integrals. So the antiderivative is going to be e to the negative 3x, but then we know we take that constant that's in front and flip it. So we get negative 1/3 e to the negative 3x. All right, so we have all of our pieces. So now let's apply the integration by parts formula. And we know our integration by parts formula, u times dv, that's the integral that we're trying to do. 2x plus 5 times e to the negative 3x. And integration by parts tells us, well, that integral is going to be equal to u times v. So let's write in u times v. And it'll help to just kind of arrange things nicely. So I'll put the negative 1/3 first, the 2x plus 5, and then the exponential part. And then we subtract and integrate v times du. So we multiply those pieces together. And what do we get when we do that? Well, negative 2/3 e to the negative 3x dx. And that remaining integral isn't too bad. So I'm going to just wait until we have all of the integration done, and I'll do the evaluation part of our definite integral here. We'll do that at the end. So I'm going to kind of save my evaluation until the end. All right, so let's keep going. And that's our step 3, really, of our integration by parts, is just to apply the formula. Next, we want to do that remaining integral. And, there's a little bit of simplifying we maybe could do. So I'm seeing a double negative in here. So if you wanted to clean that up, you could. But let's actually just get the remaining antiderivative. So we're going to have that negative 1/3 2x plus 5 e to the negative 3x. We're done with that part. Now let's get the remaining antiderivative. So the negative 2/3, that's just a constant multiple. So we'll combine that with the negative out front, so that'll just give us plus 2/3. And really, let's find the antiderivative of that e to the negative 3x. And we already did that. We already did that for finding v. So what is the antiderivative? Well, it's negative 1/3 e to the negative 3x. And we're done with the integration at this point. So we'll do the evaluation. Well, we're free to do it now, but maybe we'll clean things up just a little bit, just to help the evaluation side, so we don't have so many constants floating around. All right, so what can we do? Well, there's a few things we can factor out. We can factor out a -1/3 from both of these, and we can factor out that exponential part. So if we simplify this, we can factor out -1/3 e to the -3x. And what are we left with? Well, we're left with a 2x plus 5 plus 2/3. And then we'll evaluate that from x equals -1 up to x equals 2. And we're going to evaluate that entire thing. So let's plug in now. So when we do that, we end up with -1/3 e to the -6. So we're plugging in 2. We're plugging in our top number first. And then instead of the 2x plus 5 plus 2/3, when we plug 2 into that, we get 15 plus 2/3. And that's what we get when we plug in 2. So then we subtract, and we're going to plug in our lower limit. So what's our lower limit? Well, it's -1, so let's plug in -1. We end up with -1/3 e to the +3. And then instead of the 2x plus 5 plus 2/3, when we plug -1 into that, we end up with 3 plus 2/3. Ooh, and that was close. Just got the answer in. Let's see if I can get that parentheses. There we go. Whew. All right, so we just fit this one in. I was sweating there for a little bit. Yeah, so really the integration by parts here, the process, it's the exact same steps. Go through, get the antiderivative all in terms of x, finish all the integration, and then the very last step, maybe you simplify it a little bit so you don't have so many terms, but then you just plug in. So it's the usual definite integral evaluation. Top number goes in first, so we plug the 2 in first. Bottom number goes in second, so we plug the bottom number into our antiderivative, and then we subtracted, so we found the difference. And I mean, maybe there's a little bit more simplifying we can do here, but this is fine. This is our this is the value of our definite integral. So, like we said, the integration by parts is all going to be exactly the same. All the steps, all the strategies are going to be exactly the same. The only thing extra here is the evaluation. And so you have some choice. And I kind of like this approach where you just wait until you get the antiderivative and then just evaluate everything all at once. Let's try another example just to make sure that we can see what we're doing here. So for this one, we're going to integrate the inverse tangent function from 0 to 1. And this is an inverse function. So we looked at an example similar to this in one of our indefinite integral lectures, and that was where we saw how to integrate natural log. And so the same strategy we use there, we're going to use it here. So we want to recall our strategy for inverse functions. So when we're just integrating an inverse function just by itself like this, similar to what we did for natural log, our strategy was to rewrite this. It's sort of a trick, but we want to rewrite this as a product. So we'll rewrite it as inverse tangent x times 1 dx. And so rewriting it as a product like that, we go through and we identify the parts of our function. So we have this inverse tangent part, and we have this algebraic part. And so if we go to our usual acronym here for how we choose u and how we choose dv, we have an inverse trig function as one of the parts, and we have an algebraic function as the other part. And if we remember, the ones further to the left here is what we pick for u, and the one further to the right is what we pick for dv. So when we go to kind of step 1 of our integration by parts, step 1 is to choose u and choose dv. And so we're going to let u equal the inverse trig function. And so dv is going to be 1 times dx. And there we go. We've decided on u, we've decided on dv. So the next step of our integration by parts is to calculate du and to calculate v. So what's the derivative of arctan, of inverse tangent? Well, we kind of need to know this one. It's 1 over 1 plus x squared. And then we multiply by dx. And then what's the integral of 1? Well, the integral of 1 is just x. All right, so we have all of our pieces. So now we apply the integration by parts formula. So u times dv, that's the integral that we're trying to do. And integration by parts tells us that's equal to u times v. So let's write out u times v. So I'll write that as x times inverse tangent x. It helps to put those kind of smaller loose terms like just the single x there in front of the in this case, the inverse tangent function. It just looks a little cleaner when you write it out. And then it's minus the integral of v times du. So we multiply those pieces together. All right. Sorry. So v times du gives us 1 over 1 plus x squared times x dx. So if we multiply those together. Now, that integral looks a bit complicated. There's a fraction, there's some complicated terms in the denominator, so it looks like that might require some more work. So for this one, I think it might be helpful to just kind of do the evaluation, kind of to split up the evaluation. So what we'll do is we'll evaluate the u times v part. Excuse me again, sorry. We'll evaluate this u times v part, and then we'll also evaluate the v times du part. And we'll kind of do that separately. All right, so that's step 3. Step 3 is to just apply the integration by parts formula. And let's just go through and evaluate the u times v part. See what we get. So when I plug in the 1, plug the top number in first, we get 1 times inverse tan of 1. Then we plug in our 0, the lower number, so we get 0 times inverse tan of 0. And let's clean that up a little bit. We can maybe simplify that down. And we'll save this definite integral. We'll save this until a little bit later. So we'll just kind of tuck that off to the side for now. So right now we're just worrying about evaluating this u times v part, because that remaining integral is going to require a few extra steps. And so what is... So maybe we know this. Inverse tan of 1 is pi over 4. And inverse tan of 0 is 0. So we can simplify this down a little bit. And we get pi over 4 for that entire evaluation. So we have pi over 4, and then we still have to do that remaining integral, the integral from 0 to 1 of 1 over 1 plus x squared x dx. So let's see how to do that. And that's going to require a little bit of extra work. All right, so let's keep going. So far we know that we have this integral is equal to pi over 4 minus the integral from 0 to 1 of 1 over 1 plus x squared x dx. Now when we look at this remaining integral, we see a fraction. We see something complicated inside the denominator. So we're going to use substitution rule. We see a complicated inner function. So that 1 plus x squared, that's a complicated inner function. So that's what our choice for u is going to be. So we're going to let u equal the denominator there, 1 plus x squared. We're going to calculate the differential du. So this will be 2x dx. And for substitution rule, this is where we need to kind of match up our differentials, see how they kind of compare. So if we look in our integral here, we have x dx. In our differential we just calculated, we also have an x dx, but we do have this extra constant. And so the way we handle that extra constant is we solve for, well, we divide by it. We solve for the x dx. And if we do that, we get 1/2 du is going to be equal to x dx. And so in our integral there, we know the fraction here, this is going to become 1 over u, because we said u was equal to 1 plus x squared. And then the x dx, that's going to become 1/2 du by what we just calculated. So let's actually go through and plug all of that into our integral, just like we would with a regular substitution rule problem. So we're done with that pi over 4. We're going to have 1 over u times 1/2 du. And we have a little bit of control over what we do with the limits of integration. So let's actually convert those limits of integration. So if our upper limit was not u equals 1, it's x equals 1, and our lower limit is x equals 0, we plug these into our equation for u, and so we get u equal to 1 plus 1 squared when we plug the top number in, which is just 2. And then we get u equal to 1 plus 0 squared, which is just 1. So our new limits of integration, once we convert this over to an integral all in terms of our substitution u, is going to be from 1 to 2. All right, we're almost there. So it's looking good. Now we just need to know what the antiderivative of 1 over u is. And that's absolute natural log absolute value u. And then the 1/2, that's just a constant multiple, so we can put that in front. Now for the evaluation part of this, we've already evaluated that pi over 4 in front. So we're just going to evaluate this 1/2 natural log absolute value u. So maybe that's the only thing that can get a little tricky if you're doing your work here. You've evaluated that first part. You want to kind of keep that separated. The pi over 4, you want to keep that off to the side. And we're only going to evaluate, our integral here. So we found the antiderivative. We only want to evaluate just that antiderivative. All right, so let's see what we get. So let's evaluate the 1/2. We'll plug the 2 in. Plug the 2 into our antiderivative here. We get 1/2 natural log absolute value 2. And absolute value 2 is just 2. Minus 1/2 natural log absolute value 1. And absolute value 1 is just 1. And we know natural log of 1 is just 0. So this whole piece, this whole second part here is going to be 0. And cleaning this up, simplifying it down, we get pi over 4 minus 1/2 times the natural log of 2. And so that's the actual value of this entire definite integral. So there we go. So, really the only thing different here, the integration by parts techniques, the strategy is all the same. The only thing different here is how we handle the evaluation. So we have a little bit of control over where we evaluate things. So for this example 2, we evaluated our u times v first, and then we had this remaining integral, which required a little bit more work, so we kind of went through and evaluated that second. You could kind of do it that way. Or, like we did in example 1, we just went through and did all of our integration, got our antiderivative all the way back in terms of x here, and then once we were done with everything, all our integration, then we evaluated at the very last step. So whichever method you want to use, perfectly fine. So it really comes down to what you prefer. You'll get the same answer regardless. All right, so I think that'll do it for today. Next time we're going to move into techniques on how to evaluate trigonometric integrals. So we're going to kind of switch gears a little bit, but it'll still be kind of integration strategies. So we'll see that tomorrow. All right, we'll see you then. Bye-bye.